All right, so as promised, we're going to go ahead and look at trying to compute this matrix a to the 83rd power. So if you're picking up a little bit later, we're looking at this cute little graph. Let's go back to one of these ones that don't have any doodles on it. And we have this graph on 10 nodes and on, what do we say, 16 total edges. And we're going to begin counting the number of paths that are going to start at a location and end at a specific location with a specific length. So here we had length of 3. Now we're upping to the ante to looking at lengths of 83. So we already know how big this number is going to be. It blows up and becomes fairly awful in a hurry. But we want to chat about how we can actually compute that somewhat efficiently, which is actually a really cute little algorithm that has kind of creepings into all sorts of other things. Basically, anytime I have to do the same operation over and over and over and over again, I can actually streamline that in a very tidy fashion. And what it's going to do is it's going to make use of this kind of base 2 structure of 83. Because building up powers of 2 is actually really, really easy. So if you've ever seen the modular exponentiation algorithm, the power mod function, if you've ever seen it like that, that technique is identical to this process. Officially, you'd maybe see that one in like a Math 201 course, and now we're going to see this one now, and you can say like, oh, this is the exact same algorithm. That's really cool. And then the idea is that that same structure of this algorithm resonates over and over and over and over again. Anytime you have to do the same operation a bunch, you basically blast the number of times you have to do that operation into a bunch of powers of 2, and then sew things back together afterwards. So it's a really cute idea that's not just a cute little one-off here. It's a thing that we'll constantly circle back on over and over and over again. Okay, so let's go into it. So a to the 83rd, again, kind of a dumb power, but it's big enough to be interesting while also not breaking my brain completely. So computing a to the 83rd power is pretty easy when I start thinking about how can I just genuinely compute large powers. So if I'm given one of these giant arrays a, I can compute a squared by taking a times a. I can compute a to the 4th by taking a squared multiplied by a squared. I can compute a to the 8th by taking a to the 4th times a to the 4th. A to the 16th then is easy. A to the 32nd is easy. A to the 64th is easy because I'm just multiplying those previous terms together. So you can see that there's this nice recursive structure, is that you're always just computing the next power of 2 by multiplying together the last 2 terms. So very, very quickly, I can actually generate a to the 64th power. In total, I had to do what? 1, 2, 3, 4, 5, 6 total bits of matrix multiplication. So in our little matrix that we had here, there were 10 vertices. So each of those multiplications required 1,000 multiplications. And now I'm telling us that we have to do this 6 times. So in total, to compute a to the 83rd power, I had to do 6,000 pieces of multiplication, which obviously a computer is going to do in a snap. But if I wanted to change that 10 to 10,000, obviously things are going to start slowing down a little bit. But it's really, really fast. And it's much faster than if you were thinking kind of old school ways of being like, well, to get to a squared, it's a times a. And to get to a cubed, it's then a squared times a. And to get to a to the 4th, it's then a cubed times a. And a to the 5th is then a to the 4th times a. Because you have to do a whole bunch of multiplications to build up to 64. So by leveraging this kind of power 2 structure, we can ratchet up to 64 very, very quickly. And you can see exactly the number of multiplications we need are going to come from that power of 6 that emerges from the 64. So in total, the number of matrix multiplications that we have to do to construct a to the 64th is going to be this 6, which is just log base 2 of 64. In general, if I want to raise something to the nth power, it's going to take about log base 2 of n number of matrix multiplications. Each of those matrix multiplications are then going to require n cubed number of just basic multiplications. So it's depending on how you're counting these things, is that it's going to be running in logarithmic time if I'm counting the number of matrix multiplications, but it's going to be this log times this n cubed if I actually want to convert it to just basic regular multiplications. But you're going to see that this adds one just extra little piece out in the very beginning of it. So it's super fast in order to create large powers. If I wanted to create a power of 128, I just have to do one more little bit of multiplication. If I want to ratchet it up to larger and larger powers of 2, I don't have to go many more rows beyond this. Kind of ran out of room, but You can obviously see the 128 would be really easy. The 256 would then just be multiplying those previous terms, and so on and so forth. The problem, though, is that 83 is not a power of 2. But I can write it as a sum of powers of 2. So 83 is in fact 64 plus 16 plus 2 plus 1. So 64 and 16 obviously adds up to 80, and 80 plus 3 is then 83. So computing a to the 83rd power is then computed by taking a to the 64th multiplied by a to the 16th multiplied by a squared multiplied by a effectively to the 1. So when I have powers like that are then going to be added together when I multiply them. So some properties of exponents. So if we have x to the a and x to the b, this is then x to the a plus b. And here you can start to see where this nesting structure is going to be really nice. So in order to compute this product, I'm basically going to build them up as I go. I'm going to start with the a, then I'm going to multiply in the a squared, then I'm going to multiply in the a to the 16th, then I'm going to multiply in the a to the 64th. So I never have to, leave just the multiplication of two matrices world. I'm always going to just have a matrix multiplied by another matrix, and then I might just have to do that operation a whole bunch. So if you go back and kind of think about the total number of matrix multiplications that I needed to do, well, to compute a to the 83rd, I had to get up to a to the 64th, which required 6 matrix multiplications. And then when I sewed everything back together, I'm going to pick up 1, 2, 3 more of them. So I had 6 plus 3 more, which makes 9 total matrix multiplications, each of those obviously requiring 1,000 multiplications. But you can see that it doesn't add up a ton. So getting to that power of 83 is only going to add, an extra little factor in front of that n cubed structure. There's a couple other little delicacies that we need to begin looking into, basically how we're actually going to implement this. So when it comes to the actual implementation, it's basically going to be this kind of back and forth structure, is that I'm going to start with kind of the smallest power inside of that a to the 83rd, which is the a to the 1 term, which is this very far right thing. And then I'm going to sprinkle in the a squared, then I'm going to sprinkle in the a to the 16th, then I'm going to sprinkle in the a to the 64th, which is exactly what this little chain was trying to represent. What I want to do then is while I'm building those things up, I'm going to be creating the next power of a that I need. So they're going to be happening simultaneously. I'm not going to build this whole blue list and then come and build this kind of nested structure because I maybe don't know how far I need to see this thing. So I'm going to be doing these things in tandem. So I'm going to have my a. So I need the a because my little formula says I need to. And then I'm going to build a squared. Then I'm going to multiply in the a squared because my formula says I need an a squared. And then I'm going to build up a to the 4th. I don't need the a to the 4th, so that left-hand side isn't going to update, but I need the a to the 4th in order to compute the a to the 8th. I don't need the a to the 8th because my little formula up on top says I don't need an a to the 8th, but I do need the a to the 8th to create a to the 16th. Then I'm going to see that I do actually need the a to the 16th, so I'm going to multiply that in, which is right here. And then I'm going to use that a to the 16th to actually generate a to the 64th. Well, actually generate a to the 32nd. Jumped ahead of myself a little bit. I don't need the a to the 32nd on the left-hand side, but I do need the a to the 32nd to actually create a to the 64th. And then on my very last pass, I'm going to add in that a to the 64th. I'm going to multiply it in, I guess. And then if I needed to, I could create the next power of a, which is a to the 128th, but I don't actually need that thing because I've created all of those things. So there's kind of two things that are happening in tandem. I'm going to have my formula, basically, I'm going to need 64, 16, 2, and 1. That's kind of my recipe if you want to think about it like that. And then I'm going to create all of my ingredients over on the right. I don't need all of the ingredients, but I do need them to generate the next thing. If I never created a to the 32nd, I would never see a to the 64th. So even though I don't need the 32, I need it to create the 64. So that's where we're going to have these two things kind of coexisting. So what that's going to look like in our actual implementation is going to be some big outer loop that's going to kind of strip off these things as we need and then build up the next term as we go. So how we strip off the things that we need basically boils down to how do we create this special little formula? So how do we get the 83 and convert it into 64, 16, 2, and 1? Hopefully just a binary thing is screaming at you. And if it's been a little while since you've actually converted things to binary, it's worth just a 1 second kind of reminder. So 83 is 64, 16, 2, and 1, which are obviously 2 to the 6, 2 to the 4th, 2 to the 1, plus the 2 to the 0. So padding in the extra missing zeros, we get 1, 0, 1, 0, 0, 1, 1. And if you've never done this through division, the way that you can actually achieve those things is by constantly taking your initial number, 83, dividing it by 2, and then taking the resulting quotient and then dividing that by 2 over and over and over again. The resulting little remainders then, the little trail that we're going to leave, then become exactly the binary for that particular number 83. So 83 divided by 2 is going to leave you a quotient of 41 with a remainder of 1. So that little 1 that emerged here is then that little 1 right there. That corresponded to this little 1 right here. And that's actually how this whole process is going to start, is that we're going to take the 83, we're going to divide it by 2. If it's going to leave a remainder of 1, that's going to tell me that my formula, kind of my recipe, needs the A term. So that's going to blip. So it's going to be a little if structure that says, definitely go use that A, add it into my later thing. Then we're going to re-update all of those kind of things to start the process over again. So 41 divided by 2 is then going to also leave a remainder of 1, which is where that 1 comes from, which is where that 2 comes from, which is then going to go back to my little recipe, and it's going to say, yep, definitely need that 1, so multiply it in to create the A cubed. Then we're going to have a couple rounds where nothing happens. So when I divide it by 2, it's going to leave a remainder of 0, which is where that 0 comes from, because there's no 4. Then we're going to divide again, which is where that 0 comes from, so there's no 8. Then we're going to divide again and see a remainder of 1, which is where that 1 comes from, which is where that 16 comes from. So my recipe says, yep, I definitely need that. So that's where this row then occurs. Then we're going to do one more bit of division. So take the 5, or take the 2, divide it by a 2, which gives me a quotient of 1 and a remainder of 0. So we don't need the 32. But we do need the 32 to create the 64. And then on my very last pass, we're going to take that. We're going to see a remainder of 1, which is where that little 1 comes from afterwards. So it's a really tidy way to obviously extract the binary thing out of that. And that's how I'm actually going to implement this thing, is that it's going to eat a matrix A, and it's going to eat the exponent of that thing. But that exponent is going to be stored base 10. If you wanted to, you could automatically convert this thing to binary and then use that as my little recipe, yes, no guide. I actually have an implementation that then converts that thing as we go. Basically, it's going to start off with an R value of 83. The very first thing it's going to do is going to take that R modulo 2, which we see is going to kick out a 1, which is where that little 1 is then going to come from. So we're just going to constantly reduce this thing modulo 2 to see what's going to happen. Then my R is going to be restored as a 41, and then we restart that process over and over and over and over again. So it becomes this kind of cute little guide as we see fit. So the actual algorithm, which I kind of spoiler alerted to it before, is really short. There's a big while loop that says keep on doing this thing as long as my exponent still has some meat to it. So that's going to be run with a while loop that then terminates once my R goes down to a 0. Then there's going to be this question of, does it meet my kind of formula or my recipe? So that's going to be that if my R mod 2 is a 1, then I'm going to multiply by my next term. Otherwise, don't do anything. So if you remember back to this game, there was this back and forth. Not every single time did I actually update the stuff on the left. I only updated it when I needed it to. So I'm always going to, multiply in the next term if it's needed. So I started with the A because it told me to start with the A. Then I multiplied in the A squared. Then I didn't do anything. Then I didn't do anything. Then I multiplied in A to the 16. Then I didn't do anything. Then I multiplied in A to the 64. So that's what's going to occur in this if structure, is that if my recipe says I need it, I'm going to update my new little product, which I'm currently calling a B, by multiplying in the next term. So the next term here are going to be stored as little a's. So my little a starts off as just being the A. And then along the way, it gets multiplied by itself to generate, first a squared, then an a to the fourth, then an a to the eighth, over and over and over. Notice that that occurs every single time. Again, to create the 16, I needed to have 8s. To create the 32s, I needed the 16s. To create the 64, I needed the 32nd. So that was that right column, is that that's constantly going to be re-updated. So we have that first test that's going to say, do I meet my formula requirements? If so, then update. Then you're going to constantly generate the next term. And then at the end of that run, we're actually going to do that division. So it was 83. I'm then going to divide it by 2 and then turn that R into a 41 and then restart that process over and over and over and over and over again. The one little caveat that needs a little bit of additional flushing out is how do we actually start the kind of process of generating the B. So in our scenario, we started with our little A, but that was nice because we had an A to the 1 term. If I didn't have that last A thing, I would actually start at a squared, but I wouldn't necessarily know that that's where it's going to start. So we actually initialize our little product as being what's referred to as an identity, which is going to actually be this big array that just got ones down the diagonal. So it's going to look kind of like a 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. That thing functions just kind of like the number 1 does. If I take an A and I multiply it by that 1, it's just going to kick out the A again. So it becomes kind of our easy initialization that allows this kind of back multiplication to actually work. So it does all of the things that it needs to do, but that's the one last little bit of annoyance that we have to kind of poke into as we try to create this whole little machine. So I think I'm going to pause it there, and then we'll jump into the actual implementation, play around with the a to the 83rd, and again, play with larger and larger powers and see how far we want to take that. So I'll give it a pause, and then we'll jump back.